So reflections. A quick look here. Well, yeah, one light. Turn on the light.
No.
Oh.
Turn it back off. Yeah, turn it back off.
Okay, so now we can see it. Okay. So one type of transformation we already mentioned, reflections. So reflections. We're talking about reflections in Euclidean geometry. Reflections are over something linear, right? So a line. It could be a reflection over a ray. It could even be reflection over a segment, but it's got to be a reflection over some type of linear thing. We can call that line, sometimes it's called the line of symmetry or the axis of symmetry, but it's what's going to equally divide the pre-image from the image, right? And we'll look at some pictures of that in a second. So, definitions: a reflection in a line M. So this is line M. I guess we need to probably write that on there. A reflection in line M is a transformation such that regardless of which point we're talking about on the pre-image, we're going to call it point P. If it's a reflection, that's got to map to some image of that pre-image. Remember what we said on Friday? Whenever we put a prime next to something, that means it's undergone a transformation. In this case, a reflection. So it started at P. A prime means that it's been changed, and that's really consistent in mathematics. We'll use that prime notation in calculus. We use it a bunch for slightly different kinds of stuff. But it always implies that there's been something that's been done to change the original to create something from it, right? So these are the properties that have to be true if it's a reflection. Let's see if you can tell me what has to be true. If P prime is a reflection of P, tell me some stuff that's got to be true. What's one thing, Elton?
P prime has to be equal distance from M as P.
Okay, so one thing that would have to be true is that we could say those segments have to be congruent. So let's go ahead and say that this point right here, let's call that point O. Okay, so we'd say that PO would have to be equal to P prime O, right? That distance has to be the same. Yes, ma'am?
It's 180 degrees away from it, right?
Okay, good. So then these would have to be, line M would have to be perpendicular to the line joining pre-image P and image P prime. Another thing that has to be true. Okay, what else?
Would PM be equal to P prime M?
Okay, well, so in this case, okay, M is, yeah, what's that M mean? It's a line, right? So it's not, in this case, M refers to the entire line instead of all the points on the line. So if we pick, but you're right, if we did pick a point on line M, then P and P prime would have to be equidistant from it. And that's the case because line M is a what of segment P prime? Perpendicular bisector, right? Okay, does that make sense? Okay, so you got them. Those are the properties. Now there's going to be
7 more properties when you have them.
no, that's it. So if P is not on M, then M is the perpendicular bisector of P prime, of that segment, right? And really, these PowerPoints don't do a very good job of this, but that's supposed to be a symbol on the top indicating it's a segment. Okay?
Who made these PowerPoints?
Another teacher. Okay, so then what happens, oops, didn't want to go that far. So what happens if the point P is actually on the line of reflection? Because that'll happen.
Oh, no.
They'd be the same at the same spot.
Yeah, they're the same point then, aren't they? Right? Okay. So if point P is on the line of reflection, then P prime and P are coincident.
And how come if a prime says that it changes, it doesn't really change at all?
Well, okay, in that
It could have been
one
a
case,
360 degree
it doesn't, the only reason it doesn't change is because it maps to itself. Let me maybe illustrate that. So if we have, for example, let's say we've got, here's our line of reflection, and here's the object that we're going to reflect. Let's start off by reflecting that. So what am I going to get back? I'm going to get a mirror image of that, right? So I'm talking about the shape, not the letter, right? If I reflected this shape over the line, I get that, correct? Okay. What if I reflect this shape? What's that going to give me if I reflect that one? It's going to cross over. Part of it is, right? But we might be able to make this simpler by looking at just the individual vertices, and then we'll just sort of connect the dots once we've reflected those 3 vertices over. Okay, so let's label these. Let's call this one A, B, and C. So where is vertex B gonna end? B prime gonna end up? To the which side? To the right, and it's gonna have to be. So if I were to create a perpendicular line here, it's going to have to be the same distance away from the line on the perpendicular bisector. So everybody agrees it's going to be about right there. So that's going to be B prime. What about A prime? Well, same thing, right? So A prime is going to end up right about there. Does that look good? Okay. So there's A prime. What about C prime? It goes on the left side, right? So C prime is going to end up like right about there. And if I connect those, look what happens.
That is a really disgusting color.
It's a reflection. I didn't draw it very well, but it's a reflection, right? So it reflected over, but parts of it, does that make sense? So what happened to the parts, like what about all the points, only 2 in this case, what about those points like right there and right there? When they got reflected over, the figure changed, right? And going from purple to green, we got a different, the reflection is clearly a different shape than what we started with, a different figure, right? A couple points, though, during that process of reflecting, just didn't get moved, right? Are they different points? It's a matter of semantics, really. I mean, are they? In a way they are, because they're parts of a different shape, right? You see my point? So even though, like, P prime and P prime happen to be lined up with each other and they're coincident, you know.
They're in the same place.
Yeah, they're in the same place, but they could be parts of a bigger whole that have been reflected. So it's probably best to think about them as being still image and pre-image. I mean, they're still separate things in a way, right? They just happen to line up. Does that make sense? Okay. All right. Okay, so let's look for some properties here. Okay, let's look for some properties. So what if we want to graph the reflection of H? And when we talk about a reflection in the x-axis, that's a little bit of weird terminology. It almost seems like it should be a reflection over the x-axis. And that would be an okay way to say it too. But in math, a lot of times when we talk about a transformation, we talk about a transformation in whatever the vehicle for the transformation is. In this case, it's going to be a line of symmetry, right? So it makes sense that where is the answer going to be? If we start off with H, which is at point 2, 2, where is H prime going to end up? Okay, 2, negative 2, right? And we know that because it's a horizontal line, the line of reflection, so it's going to move vertically, right? And it has to be the same distance away from the line. Does that make sense? Okay. What if we're going to do something a little different though? What if we're going to reflect the point H in a different line? Okay, we can do that, right? We don't have to reflect it over an axis. We can reflect it over anything. So what if we want to reflect the point H? Let's do H first. Over the line y equals 4. What do I end up with? 2, 6. Everybody see that? Okay. So this time it's gonna end up right there.
Oh, okay.
Does that make sense? If we did that instead? Okay, we still get the same properties. Notice that H and H prime they're on a line that is perpendicular to the line of reflection, right? The line of reflection is a perpendicular bisector of the segment connecting the points. So these distances those segments are congruent, the distances are equal. Yes, Emma?
Could you do reflection over a diagonal line?
You can. You can do reflection over any line. It gets a little more complicated if you do reflections over diagonal lines, but you can.
Oh, mine, not real.
Well,
So, the points like H, it'll always be on the same. Yeah, the same. What?
have the same x coordinate?
Yeah.
Okay,
Well,
only
not that,
because
but like, yeah.
only because we reflected over a horizontal axis, right?
But if we went over a vertical.
Okay, let's do that. Yeah, what would happen if we were to reflect these over a vertical axis? Like, let's say we reflected H over the y-axis, right? Then we'd end up. I mean, this is kind of off the graph here, but would you agree? Then we end up like right over there at H prime.
So it'd be on the same. Yeah.
Yeah, in that case, the y components would stay the same, right? The y coordinates would stay the same, and the x would change. But what if it's like the line of reflection is at some bizarre angle? Then everything's going to change, right? Okay, and that gets a little more complicated. We'll talk later about how can we predict where the coordinates are going to be. Yep.
You go over a curved line?
You can't. Nope, you can't. Reflections can only occur over something that's linear and therefore straight. Okay. What about part B? If we want to reflect point G over the line y equals 4, Matthew, what are we going to get? What are the coordinates of G prime?
Negative, or 5 negative 4.
Okay, I'm reflecting it over the line y equals 4. So that's going to be that light green line, right?
Then it would be itself. wouldn't
It's
it?
itself, yeah. So the coordinates of G prime would just be 5, 4, right? Stays the same. All right. Okay. Okay, so let's see if we can come up with some generalities here. Whenever we reflect, and you guys already saw this, whenever we reflect a point over the x-axis, right? If we reflect it over the x-axis, which is a horizontal axis, the movement of the point is going to be vertical or horizontal? Vertical, right? It's going to be vertical, and it's going to end up, the x-axis is going to be the perpendicular bisector, right, of the segment connecting the two. So what's always going to be true? Every time, if I reflect a point over the x-axis, how can I predict the coordinates of where it's going to end up?
X will stay the same.
X stays the same, and the y coordinate, I know what you're saying. It flips, right? It becomes the opposite, right? So we're just going to multiply the y coordinate by -1. Okay, does that make sense? What about if we're going to reflect something over the y-axis?
And the y stays the same and we.
Yeah, so we're reflecting over a vertical axis. It's going to move horizontally. The y coordinate stays the same. The new x coordinate is going to be the opposite of the x coordinate of the pre-image, right? Make sense? Okay. So reflection, we already said, is an isometry. To prove that, you know what? We're not going to do this today. We're a little short on time. We're not going to do that. Okay. I can do that. One other thing I wanted to show you. Can't remember if it's on this one or not. Okay, yeah, this is it. Okay, what happens for something, so what about something like this? What if I've got a line of symmetry? Let's make it a vertical one. Okay, what if I reflect this figure over that line of symmetry?
Oh, we're good, same.
Same, okay? It's the same. What if I reflect it over this line?
But if you label them, that you label the points, that they'll be in different places.
Yeah, that's true.
So it's
What if I reflect it over that line?
similar.
It's the same. Pretty good at that.
It's not the definition of symmetry.
Okay, so are there any other ways I could do that?
No.
There's no other way that I could reflect that blue rectangle over a line and have it line up. What does that tell you about something unique about a rectangle?
It has one line.
Yeah, it has two lines of symmetry. Okay. The number of lines of symmetry is defined by how many different ways you can do that for an object, right? Does that make sense? How many ways you can reflect it over a line and have it line up with itself, right? What could I do to that? Okay. Name a figure that has a quadrilateral that has the same amount of symmetry as a rectangle, but that looks different. Okay, a square, does a square have the same amount of symmetry as a,
Yeah,
It doesn't go as four.
square has, how many square has four?
because if you cut it like this,
Diagonal.
yeah, diagonal.
So like up and down.
So what are the lines of symmetry of that square?
Up,
Okay, we got, it is a rectangle, right? So it should inherit all of the lines of symmetry from the rectangle.
but also like the others.
So we got that guy, that guy. What else do we get?
Diagonal.
Okay, we also get diagonals, don't we?
What if we had like an octagon or something like that?
Okay, well, we'll look at that. So that one's got four.
Octagon.
Okay, but that wasn't my original question. I want to know, tell me a quadrilateral that has the same number of, so two, the same number of lines of symmetry as a rectangle.
Rhombus.
Rhombus.
What is it?
I know what a rhombus is. What's the definition of a rhombus?
All sides are equal.
Both side diamonds.
It's like a triple.
Okay, all sides are congruent, right?
You never noticed that?
So what would the lines of symmetry of this be?
The diagonals.
Yeah, diagonals. Okay.
And then square is also a rhombus, right?
Square is also a rhombus. So a square gets both of those, doesn't it? Because, does that make sense? It gets the properties of the rhombus and the rectangle.
Then you would have four.
Okay. It seems fitting that on today we would get this question answered. What is, there we go. Which two-dimensional figure has the most symmetry?
Circle.
Okay, how many lines of symmetry does a circle have?
Infinite.
All right. Okay.
I was trying to think of like.
Okay, how many lines of symmetry, trick question, how many lines of symmetry does a hexagon have?
No, just kidding.
One.
Depends on the hexagon.
Four?
Okay, now it can't be infinite, there's gonna be an upper limit, but
Six.
6,
What's the like?
What is it?
12.
No, what's
Wait, what is
the
hexagon? Can you draw it real quick?
sure,
Yeah, can you draw real quick, man?
I can.
What's the trick to like? There's no three.
Oh, how many sides?
Okay, I've heard a lot of correct answers and they've all been different, how come they're all working?
It depends on the hexagon.
It depends on the hexagon, doesn't it?
Oh, yeah, it's not perfect.
Now, when I said hexagon, you probably assumed a regular hexagon,
Yeah.
right? So a regular hexagon looks like this.
Is that
That look pretty regular? Pretty regular.
Six-sided shape.
Okay, raise your hand if you got the answer. How many lines of symmetry does that have? What do you think?
12.
12? How'd you get 12?
I took all the corners and all sides.
Okay, so,
That one.
are you sure? So there's 1,
It'd be six.
Because there's 2 points for every line of symmetry.
Does that make sense?
There's 2 sides for every line of
Okay.
symmetry.
So we're gonna get 6.
So it'd be 6.
Yeah.
I'll trick you out.
Okay, 6. It doesn't have to be that though, does it? What's the least that a hexagon, what's the least number of lines of symmetry that a hexagon, not necessarily a regular hexagon? 0.
It could have
Could have 0.
Negative.
Okay, here's a tricky one. Here's a real tricky one. What about maybe it's not, I think it's country. What about a pentagon? So, well, okay, what's the most a pentagon can have?
5. 5.
5.
5's right.
5.
That's right.
So what's the trick then?
Well, I thought people might
Yeah.
think that was a little different because pentagons don't have an even number of sides, so I
Because
can't.
your point right in the middle
Right,
of the
exactly.
side.
Exactly.
But triangles don't have 3.
Yeah, they do.
Yeah,
They do?
Yeah.
a regular, an equiliteral
Oh,
does.
yeah, okay.
Everybody see that?
It's how many sides it has that determines?
Oops.
Oh.
Yes. It's the number of sides that determines the amount.
Not all.
Yeah, that each regular polygon has.
You get the idea? We can just do this, right?
My God.
And so on and so forth all the way around. Triangle will be the same thing.
Yeah, I forgot. I'm trying to believe that
Almost
corner
at
of it.
So do you think could anybody propose then any regular polygon? Square had 4, didn't it? Right?
Why is it a color? Oh, the number. Wait,
What do you
they
think it
just-
is? What do you think the maximum number of lines of symmetry is for a regular polygon? Number of sides.
No, a tetra, it'd be a tetragon.
Why don't we call it a tetragon?
Because
Which
it's
one?
A
fancy.
square or a rectangle?
I don't know. Good question.
Let's
Good
just
question.
all the more squares, tetragons from now on.
Create the mascot.
And why is it?
Good question.
Good.
Okay. All right. Man, I gotta take roll. We're done.